In this video we are going to study the 4 laws of black hole mechanics. It is possible to establish an analogy between these 4 laws and the 4 laws of thermodynamics. The zeroth law of the constancy of the temperature across an object which is in thermodynamical equilibrium. The first law that tells you how the energy changes when other parameters change. The second law that tells you that the entropy always grows, and the third law that tells you that it is impossible to reach zero temperature by a finite number of steps. Before we establish these analogies, an analogy which gives rise to what is called black hole thermodynamics, we have to find why or what are the quantities which are analogs to the temperature, the energy, the entropy, and so on in a black hole. The first quantity that we are going to study, and which will be the analog of the temperature, is called surface gravity. Okay, we have almost seen it before. In fact, we have dealt with it without calling it by that name. And we are going to introduce it for the particular case of static spherically symmetric black holes. Suppose that we have a black hole solution which is described by a metric of this form. This is completely general for static spherically symmetric, as we proved, because we are going to consider this capital R squared, okay, not just the function lambda. As we have said, for static black holes, the apparent horizon, the Killing horizon, and the event horizon coincide, and the only Killing vector whose Killing horizon makes sense, it could coincide with the event horizon, is the Killing vector that generates time translations. This is, in these coordinates, just ddt. And remember that k squared is just ddt automatically, and this is what we call lambda. So the place where the horizon might be is the place where this lambda vanishes. Okay, this is where the Killing horizon will be, and this will coincide with the event horizon. If lambda vanishes at the different values of r, which is what happens for the Reisner-Nordström black hole, the event horizon will be the one corresponding to the larger value of r, the one closer, if you want, to the asymptotic region. Okay, so if suppose that there are different values for which it vanishes, okay, and we call r plus the largest of these values, and we can expand the metric, the whole metric, around that value. So lambda will be lambda of r plus lambda prime evaluated at r plus times r minus r plus terms of second order in r minus r plus square. Then we can do the same for r. Okay, this is kind of trivial. And then by assumption, okay, r plus is where the Killing horizon is, which is the event horizon, so this is 0 by assumption. And we are going to assume also for the moment that lambda prime is different from 0 at r plus. Then we will see what happens if it is not. But suppose for the moment that lambda prime of r plus, evaluated at r plus, is different from 0, and then we approximate the metric, okay, near r plus by lambda prime evaluated at r plus, r minus r plus, dt squared minus, and here we have the inverse. Yes, take the leading term. Minus, and the leading term here for r is just r squared of r plus, which will be some constant value Suppose that we are using coordinates in which r plus r squared of r plus is different from 0. If it was 0, then probably this would not be a horizon, because when this angular part of the metric vanishes, it disappears from the metric. This is typically the sign of a curvature singularity, so that case will not be included in our considerations. Now we want to rewrite this part of the metric in coordinates such that this is dr squared by definition. Okay, so if we want to change coordinates, we take the square root of this. This is lambda prime r plus r minus r plus, and the square root equal to 0. Since this is just a constant, this is a square root, or the integral is a square root, okay, and a factor of 2. So the integral of this gives you 2 times the square root of r minus r plus, and this is divided by the square root of lambda prime of r plus, which is a constant, and this is rho plus some constant, okay, and this I'm going to choose this constant equal to 0, because I am not going to worry about the asymptotics, because I am approximating the metric near the horizon. So this approximated metric near the horizon does not need to be asymptotically flat. Okay, if we square this, we get r minus r plus is equal to 1/4, so the factor of 2 dividing on the other side, and then lambda prime at r plus multiplied by rho squared. We can substitute this here. Okay, and obviously, well, here and here, and well, lambda prime r minus r plus is 1/4. Lambda prime evaluated at r plus squared dt squared minus the rho square, sorry, and there is a rho square here, minus the rho square by construction, r capital R square at r plus, which is some constant, and this is what you get. Okay, maybe we should put this 4 inside of the square, so this is just this square. And now you can compare this metric with the metrics you know, and you conclude that this is the metric of a two-sphere of radius capital R evaluated R plus. This will be the radius of the, well, better said, the horizon will have an area 4 pi r squared of r plus. This is the meaning of this. Okay, it is spherical, and if you remember one of the older lectures, this is nothing but Rindler spacetime. Which is just a piece of Minkowski. Okay, and you compare this metric with the metric of Rindler, you find that the acceleration, the parameter that gives you the acceleration here, is lambda prime evaluated r plus divided by 2. This quantity, which expresses more or less what is the acceleration at the horizon in this analogy, or in this limit in which we represent the metric near the horizon, and it turns out that it gives you Rindler. This is denoted by kappa, and this is the surface gravity of the event horizon. Okay, so this is one of the simplest ways to compute the surface gravity if you have the metric of a static black hole as here. Okay, the conclusion is that also that the near horizon limit of any non-extremal, okay, has to be non-extremal because the characteristic of extremal black holes was the coincidence of two horizons, or the coincidence of two zeros of the function lambda. So the zero that you get should be of order 2, not of order 1 as here. In other words, lambda prime should also be 0, and then you would have to take a term of second order in r minus r plus. So this kind of black hole that we just considered with lambda prime different from 0 is a sub-extremal, non-extremal black hole. And you see that we just showed in a very simple context that sub-extremal black holes, which have, as we know, bifurcate horizons, have also a non-vanishing surface gravity. So this is one of the lessons that you learn. Also that approximately the near horizon geometry of these black holes is Rindler space-time times a two-sphere. A difference with the near horizon limit of extremal black holes that we are going to study next, but that we also studied in the Reisner-Nordstrom case, Rindler times a two-sphere does not need to be a solution of the equations of motion. In general, it is not of the Einstein equations. Okay, still, it tells you what is the geometry near the horizon. Okay, so now let's see what happens at the extremal case. So the extremal case corresponds to this equal to 0. Okay, so by definition, this means kappa equal to 0. And then the approximation is that lambda is a half of the second derivative of lambda evaluated at r plus times r minus r plus squared plus terms of higher order. You substitute this into the metric, remember, and well, you get a half of lambda second r plus r minus r plus squared minus dr squared 2 divided by lambda second r plus r minus r plus squared minus r squared of r plus the omega squared. And okay, again, we want to write this in a simple form, but the best way to do this is to redefine r so that it is you place the origin at r plus. Let's call this rho if you want. Oh, I forgot the t squared here. Okay, then what you see in this metric is that this is lambda second halves, then you have rho squared dt squared minus the rho squared divided by rho squared, and also this divided by 1 lambda second r plus divided by 2 minus r squared r plus the omega squared. And now you compare with what we studied before. This is just a metric of ADS2, the two-dimensional anti-de Sitter space-time with a radius which is the square root of lambda prime r plus divided by 2. Okay, and a two-sphere. As different from the Reisner-Nordstrom case, which was very particular, it corresponds to just Einstein-Maxwell. Then the radius of this sphere, which is r of r plus, and the radius of this anti-de Sitter do not need to be equal. And in general theories, they are not equal. Okay. Still, this is a solution of Robinson-Bertotti type, because well, it will be a generalization of it with different radii. But the important thing is that this is a completely general behavior for static black holes, and you see that when the horizon is not bifurcate, you have this double zero, it's the degenerate horizon, you have this corresponds to zero surface temperature. Okay, Our presentation of the surface gravity is adequate only for static black holes. We have worked on a particular coordinate patch in which the metric has the simple form that we wrote above, but you want, as usual, a definition which is covariant that can be used in any coordinate system. This definition is as follows. So if k is the Killing vector whose Killing horizon coincides with the event horizon, then you can compute this object, and you can prove that this is always proportional to k nu itself. The proportionality constant is by definition kappa. Okay. And well, this is a covariant definition. It is given in terms of tensors, so it doesn't depend on coordinates. Another definition, which sometimes is a bit more practical and which follows from the previous equation, you have to use properties of Killing vectors and so on. Okay, this has to be evaluated at the horizon. Okay. If you compute this in general at any point, this will not be true. It is only true when you evaluate all this expression, okay, both sides of the expression on the horizon. And if you do the same here, you just take the covariant derivative of k squared, which is also equal to the partial derivative. This is minus 2 kappa k mu. Okay, in the case that we are considering k squared is just GTT, but anytime you want to compute things on the horizon, you would like to do it using coordinates which are well defined on the horizon. These coordinates that we are using here are not well defined on the horizon because by definition lambda vanishes on the horizon, and if lambda vanishes, GRR blows up. It's just that this singularity will be a coordinate singularity as long as this is finite, as we have discussed. But clearly the coordinates are not good there. They are singular, so you have to go to Eddington-Finkelstein-like coordinates or to Kruskal coordinates. Okay, so let's do this calculation now in the case of the Reisner-Nordstrom black holes in Eddington-Finkelstein coordinates, because we have already studied them. Well, we have to change to rewrite the Killing vector in the new coordinates. Okay, the Killing vector is just this, and the Eddington-Finkelstein coordinates we replace t by v, but we keep r, theta, and phi. Remember, these coordinates are not valid on all branches of the horizon. We know that the horizon is much bigger, that it has 2 branches, but at least you can compute this on one branch of the horizon. Okay. So if you remember that v was t minus r star, then this only depends on v, and you have this, and this is just partial v. Okay, then if k mu, which is the only component, is delta mu v, this means that if I lower the index, then this is g mu alpha delta alpha v, and this is just g mu v. On the other hand, if you compute k squared, okay, since this is delta mu v, this is just GVV, and remember that this is nothing but lambda. So let us now compute partial mu k squared. Okay, this is just partial mu of lambda, and this is just lambda prime. delta mu r. Only lambda depends only on r. Well, if we take the derivative, this will give us, first I take the derivative of the denominator, or 1 over r if you want. This gives me a factor of 2 and an r and a sine, and then I can write it like this, like lambda. And then I take the derivative of the numerator, and this gives me r minus r plus, plus r minus. Okay, delta mu r. I do this because then I get it in a nice way, because now the idea is to evaluate this at r equal r plus, which is the event horizon. And at r equal r plus, by definition, this vanishes. Okay, this also vanishes. So it is as simple as this. This is r plus minus r minus divided by r plus squared delta mu r. Okay, this is one side of the equation. And now, if you compare with the other side of the equation, remember that we just computed k mu. This is g mu v, but this is delta mu v g v v plus delta mu r g r v. Okay, but now this we want to evaluate this at r equal r plus, and at r equal r plus, by definition, GVV is lambda, so it vanishes. GRV is just 1, so this is delta mu r. Okay, otherwise we would be in trouble. So if you don't evaluate these expressions on the horizon, here I didn't say it, on the horizon, then you could never match these two expressions, because there would be this term which is different from 0 for mu equal to v. Now you compare these two expressions, and the conclusion is that minus 2 kappa, this is minus, okay? Minus 2 kappa has to be equal to minus r plus minus r minus divided by r plus squared. So kappa is r plus minus r minus divided by 2 r plus squared. Okay, and well, of course, this is nothing but the derivative of lambda at r plus, as we said. You can also see here that in the extremal limit, when r plus goes to r minus, they both coincide, kappa vanishes, which is what we expect. In the Kerr black hole, or in the Kerr-Newman black hole, the Killing vector is this combination psi equal to k plus the speed of the angular speed of the horizon and the axial vector. It also becomes null at the event horizon, and okay, you can compute. Now you have to compute all the same things here using the Kerr metric, which is more complicated, but the problem with the Boyer-Lindquist coordinates that we have given is that they are not valid on the horizon. You need coordinates which are Eddington-Finkelstein-like in the Kerr metric, okay, because they will be regular at the horizon. The way to do this in the Kerr metric, well, it's more complicated. You define V in a similar way. So this is r squared plus a squared divided by f dr. Okay, this is just dr star. Okay, so this is the same, exactly the same thing. But in this case, you need to redefine this angular coordinate. So as well, otherwise you don't get a regular metric on the horizon. These new coordinates are Kerr, well, or the metric, the Kerr metric is said to be in the Kerr shield form. when you rewrite it in these coordinates. So the property of these coordinates is that when you set a going to 0, well, you recover the Schwarzschild metric, but in Eddington-Finkelstein coordinates. When a is equal to 0, this vanishes. This is still the R star, so this is exactly the same change that you do in the Schwarzschild case. Okay, well, the metric in the Kerr-Schild form is given in the lecture notes. I will not rewrite it here. And if you do all the calculations, okay, you will find that kappa is R plus minus R minus divided by 2 times R plus square plus A square. And again, in the extremal limit, kappa vanishes. Just one observation, when we talked about the extremal limit being of, when we talk about the near horizon limit of an extremal black hole being ADS2 cross S2, we were talking about the static black holes only. So the near horizon limit of the extremal Kerr is something else. Okay, it has its own name. It's just the extremal, the near horizon limit of extremal Kerr. Well, once you have defined the surface gravity in this general way and studying the properties of the definition, people were able to show that kappa is always constant over the complete event horizon. This is obvious for the, well, we just showed it for the Kerr black hole and also for the Kerr-Newman. You only have to add here Q squared. But well, this law refers to more general black holes, as long as they are stationary. Initially, the proof made use of dominant energy condition and of the Einstein equations and so on. But this dependence on the dominant energy condition was removed by Walt and a collaborator, so it is not necessary, and it is valid in a more general setting. Okay, this constancy of the surface gravity over the event horizon is well, may remind you of the constancy of the temperature over the extension of some body at thermal equilibrium. So the analogy will be that at some point that kappa is like the temperature of the black hole, and this would be the zeroth law. Okay. I will not explain what the dominant energy condition is. This is explained in the lecture notes, but we are not going to make use of it. The next quantity that we are going to consider is the area of the event horizon. In the Schwarzschild or Rayleigh-Nostrum black holes, this is, which we can write in this kind of metric. Okay, R squared lambda minus R squared d omega squared. As we have said repeated times, the area is just given by 4 pi R squared evaluated R plus. And well, you can read this in the near horizon limit. Remember that it factorizes, the metric factorizes in either Rindler or ADS2 cross a two-sphere precisely with this radius. And if you find the volume of this two-sphere, which is an area, is just 4 pi R plus squared. So what is this in Rayleigh-Nostrum, for instance, because this includes the Schwarzschild case, well, this is nothing but m plus the square root of m squared minus q squared squared. Okay, and if you go to the extremal limit, this is 4 pi q or m squared, as you want to write it. Okay. In the Papavetru-Majumdar case, the horizon is just not one piece. It is divided in several pieces, each around each black hole. So you have to compute the values. You have to take the extremal limit first, the limit in which you approach the horizon of each black hole. Okay, then you will find the value of r, and for r equals 0 or r equal r star for that particular black hole. So it's just a sum of terms of that kind. In fact, each of them should be of this form, where q is the particular charge of this black hole. So it's as simple as 4 pi and qi squared. And for Kerr-Newman, here the metric is a bit more complicated. It doesn't have this form, but you can. There is no complication in if you work in the right coordinates in taking evaluating the metric at constant r and the value of r constant time and the value of r equal to r plus, and this gives you 4 pi r plus squared plus a squared, which is 4 pi. So this is, sorry, Papavetru-Majumdar, and this is m plus square root of m squared. And if you want to add charge and consider the Kerr-Newman black holes, is something like this, plus a squared. Okay, there is, well, why should we consider this magnitude? This magnitude has a very, very interesting property that was proven by Hawking, and you can take a look at Wald's book for this particular theorem, is that the area of the intersections of the event horizon with space-like surfaces, okay, let's explain what this is. The horizon is a three-dimensional space, as we have said many times. Okay, it's a null hypersurface. If you consider sections, or well, this would be the intersections with space-like two-dimensional surfaces, so they are two-dimensional space-like sections of the horizon. For this, you can compute areas and so on, because the metric, remember, it is rank 2 over a null hypersurface. So this is the kind of thing that you can compute. And in fact, this is what we are computing. Okay. We are just using the metric that survives on the horizon. If you can do this if you don't like these coordinates because you suspect that these are not valid on the horizon, which is true. You go to Eddington-Finkelstein coordinates and take r equal to r plus. The GVV term vanishes because it is lambda. The dr dv term vanishes because r is constant, and you are left only with this angular part, which is rank 2 metric. So you take any intersection of the horizon with space-like surfaces, like with surfaces with r equal constant. These are the kind of two-dimensional surfaces for whose area you can compute, and this is what we have computed, and this is the area that the Hawking theorem refers to. Okay. Anyway, this area always grows with time. In the meantime, anything can happen. Black holes can merge. You can imagine matter can fall into the black hole. In that case, it is kind of obvious that the area grows, because it is always more or less proportional to the mass squared. But in black hole mergers, this is not so clear. Okay, the area, the theorem tells you that it is always increasing, and this tells you that there is an analogy between the area and the entropy, because it satisfies this theorem, which is similar to the second law of thermodynamics. Oh, this is the second quantity that will have an analog in thermodynamics. I have to mention another property of the horizon. In 4 dimensions, also Hawking proved that the topology is always the same topology of the two sphere. It doesn't have to be spherical, but the topology has to be the same of a two sphere. So this is you expect the deformations, for instance, due to rotation or maybe due to perturbations by external matter, but the topology is always that of a two sphere. However, in 5 dimensions or in higher dimensions, it has been shown that the theorem is not valid, and it has been shown because black holes with even horizons of different topologies have been found. For instance, with a topology of the form S2 cross S, which is a solid donut. Okay, you have this circle, and at each value of this circle you have a two sphere. Okay, this is a three-dimensional space. And well, because this is not a sphere anymore, sometimes these objects are called black rings. There are more complex objects, okay, and these ones were discovered by Roberto Emparan, who is at the University of Barcelona, and Harvey Rial. So how are these quantities related? There is a third quantity that I haven't written, is the total mass, because the total mass is clearly the analog of the energy. Maybe I should have mentioned it, but I thought it was kind of obvious. Well, Smart discovered a general relation valid for, I am going to write it for the Kerr black hole. He found that this exact relation was automatically valid, and it relates all these quantities. Okay. Plus, so we have talked about the surface gravity, the area of the horizon, but also in the case of the Kerr black hole, the velocity of the horizon, the angular velocity, and the angular momentum. Well, if kappa is analogous to the temperature and A is analogous to S, well, this looks like thermodynamical potentials, and this is the total energy. Okay, so it smells to a thermodynamical relation. Okay, but this is not just yet a first law, because a first law tells you how m varies when all these quantities vary. I have to say that also, if you consider the Kerr-Newman black hole, there is another term that you have to add, which is the electrostatic potential at the horizon times the charge. Okay, so it looks like another chemical potential that appears there. Okay, the simplest form to arrive to the first law in the context of the Kerr black hole is to consider the variation through some process, okay, or some perturbation, which m becomes m plus delta m, where delta m is supposed to be very small. The angular momentum is perturbed and now becomes j plus some delta j, okay? And the easiest way is to study how delta A divided by 4 pi, okay, which is a coefficient that always appears in these calculations, changes, okay? The simplest way to do this is we write first the area, but now remember that the definition of where the black hole event horizon was the place where f became 0. F was r squared minus 2m r plus a squared. So in particular, r plus satisfies this equation, that this is equal to 0. And r plus square plus a squared, okay, is equal to 2m r. So this is the variation of r, and well, r plus, sorry, and now you have the expression of r plus in terms of well, I'll do it, okay, to delta m r plus, although r plus as a coefficient, plus 2m delta r plus, and r plus is m plus square root of m squared minus a squared, just for the Kerr case, for simplicity. This is just a matter of taking variations, and in the end, remembering that delta a is delta of j divided by m, so this is 1 over m delta j plus or minus j divided by m squared delta m. You collect all the terms and massage them to simplify them as much as possible, in order also to recognize factors, and you find that delta a over 4 pi is equal to 2 divided by kappa delta m minus omega h delta j. Okay, this is one way of writing this result. Okay, another way is to multiply everything by kappa. Okay, and then this is just a delta m minus omega h delta j. Okay. This is only for changes inside of the Kerr family. Okay, we don't consider the possibility that the perturbations take you out of this family and you have some black hole that doesn't fit into the Kerr family. This is a restriction that will be lifted later, but in order to prove that something like this is valid for more general stationary black holes, you really have to sweat, okay? So it is not easy. In any case, first of all, you have to observe that according to Hawking's theorem, this is a positive quantity, okay? So if there are changes of the mass and changes of the angular momentum, this combination always has to be positive because of this Hawking theorem. And the second thing that we can do is to rewrite this in the form of a first law. Okay, so this would be, well, I think this form, because of this factor of 2, this is 8, sorry. So it is k kappa over 8 pi delta a plus omega h delta j. And now this really has a form similar to the first law of thermodynamics, okay, where this would be the delta of E, this would be delta S, this would be temperature, and this would be a chemical potential, and so on. What we don't know just by looking at this expression is what is T and what is S, because, well, here there is a common factor. So how is kappa related to T and how is A related to S specifically cannot be found from this. Well, we will see how this was found in a minute. What I have to mention is that this form of the first law was proven for generic stationary black holes undergoing generic quasi-static processes. Okay, and it was proven by Bardeen, Carter, and Hawking. Okay, so you have 3 laws. They conjecture that the fourth law, which is law number 3, okay, law that tells you that temperature is constant in a thermodynamic system in equilibrium is the zeroth law. Okay, and the third law that tells you that the extremality of zero temperature, okay, cannot be reached by a finite number of steps was conjectured by these people and proven much later by Israel. Also, I have to say that this law was also proven in more general cases. Regarding Carter and Hawking made use of the Einstein equations. So a generalization of this law was proven by Wald and collaborators, so notably Eiger. So they proved that in general the variation of the energy would be of this form. But in general theories, theories more general than Einstein gravity, for instance, containing terms of higher order in curvature, instead of the area, something else appears, okay, that plays the role of entropy, although we still have to normalize it. This, you should know that it exists, okay? So now, how can we identify the temperature? Well, these people, when they proposed these four laws and they observed the analogy with the laws of thermodynamics, they also said that the temperature of black holes should be identically zero, because they cannot radiate. Thermodynamical system can be put in equilibrium with the environment. Okay, this means that you have to have interchange of energy, but black holes can only swallow things. They cannot emit, at least classically. It was not much later than Hawking proved that quantum mechanically black holes can emit radiation. Okay, and if they can emit radiation, and in fact this radiation has the spectrum of the radiation of a black body with a given temperature, which is proportional to kappa, then you can say that these objects are thermodynamical systems, and that you can take very seriously this analogy. A precursor, and also to identify exactly the area with the entropy. A precursor of this work were the works of Bekenstein, Jacob Bekenstein, who died not so long ago, and who observed and insisted in this analogy between area and entropy, based on the fact that you could diminish the entropy of the universe by throwing things inside of a black hole, because then after the black hole settles down to equilibrium, well, the black hole does not have entropy, and whatever you threw inside of the black hole will have some entropy that you have subtracted from the rest of the universe. So unless you consider that the black hole has entropy, and this entropy increases when it swallows things, well, the second law of thermodynamics in general is not universally valid. You could violate it with black holes. And this entropy should be roughly proportional to the area. Well, the result by Hawking says precisely that the temperature of the black hole, which is the temperature of this black body radiation, would be, here I am writing all the constants. So this is the Boltzmann constant. H bar appears because this is a quantum process, okay, and the speed of light, okay. So if you now multiply this by c squared, so this is an energy and so on, okay, and you collect all the constants that so they make up the temperature. Okay, typically you set the Boltzmann constant equal to 1. This is a constant that just tells you what the units of temperature have to do with your units of energy, but it's natural to identify them. So Kb is equal to 1. Then the conclusion, anyway, is that whatever remains in the constants there should be delta S, delta of the entropy. And you find that the entropy then is Kb, which again you probably would like to set to 1. the area, and here for h bar the Newton constant, which was also set to 1 in all these expressions. We set it equal to 1 so long ago that probably we don't remember when we did it. Okay, and c cube. Now we should remember that this combination is exactly the Planck length square. Okay, so up to this annoying Boltzmann constant, what you find is that the entropy is equal to 1/4 of the area measured in Planck length units, which should be the natural units to measure a quantum area, okay, in quantum gravity. This is often called SBH, which reads as black hole or Bekenstein-Hawking. Well, as I said, this is the starting point of a new field, which is the field of black hole thermodynamics. Okay, now you should study what happens to this radiation. When I say radiation, and people think that the radiation comes straight out of the black hole, this is not what the result by Hawking says. You can read his paper and maybe ignoring technical details, but what he studies is that the radiation observed at infinity by some static observer outside of the black hole. And this guy observes some radiation that, of course, can only come from the black hole. But the result doesn't tell you how this radiation is produced or anything like that. Okay, it's just an observation that if you are in a black hole space-time, you will observe radiation which looks like it comes from the black hole. Okay? How it comes out of the black hole? Well, I don't think it comes out. The understanding nowadays, or the most popular understanding, is that there is a percreation just outside of the horizon, and that sometimes this percreation takes enough energy from the gravitational field, so the virtual particles become real. One of them will be emitted or will separate from the black hole, and the other one will fall inside of the black hole. And the result, the overall result of in terms of energy, will be that the black hole will lose energy, okay, because in the end you end up with the black hole plus a particle. So the black hole will have less and less energy. This process is called as evaporation. Then there are lots of questions involving loss of information in this process. What will be the final point of this evaporation process, and so on. But of course, we don't have time to talk about all this. There are many popular books which are good about this, and maybe if you keep studying in this direction, you will find out more about it, or you will discover that we don't know so much about it, and we would like certainly to know much more. Well, would be from the thermodynamical point of view. Obviously, if there is an entropy and you believe that thermodynamics is ultimately statistical mechanics, what is the statistical mechanics that gives you this entropy? What are the states that are behind this state degeneracy, which is what the entropy counts? Well, probably only quantum gravity will tell you. Okay, so there are many questions in this respect, and I think that we should finish here. There is an almost straightforward application of these laws of the whole mechanics, if you want, to the merger of black holes, for instance, because you see that the total energy, if you have two black holes which are far apart, so you can tell their masses and the interaction, you can ignore their interaction energy, and then they merge, the energy or the total mass of the resulting black hole will be typically smaller than the sum of the original masses of the black holes, because part of it will be lost as interaction energy, and part of it will also be radiated. Okay, so the overall mass will be smaller, but at the same time, Hawking's theorem tells you that the sum of the areas, which is proportional to the square of the masses, roughly speaking, has to grow. This constrains the amount of energy that can be lost in the process. And also this tells you how much one and the other, the mass or the spin can change. So you can use these kind of results to constrain the possibilities of the variation of spin and mass in black hole mergers. And this will be all for this course. I hope you don't hate me too much after these long lessons. Probably I talk too slowly when I record the lectures. I think that this may be better for you, but probably it also takes much longer to listen to me. And well, I hope that you also decide at some point to ask more questions in the tutorials, because this is how you will learn more about this.